Alright, technical pilots, I hope you are doing absolutely fine. In this part, we'll be covering flight controls. I hope you have watched all of these parts that I have uploaded till now on this channel. Firstly, we did structures, then hydraulics part 1, part 2, then we did landing gears, then wheels and tires, and then wheel brakes. If you haven't watched them, go ahead and watch them first. In this part, we'll be starting with flight controls. Alright, so let's start with flight controls. Firstly, we have the three axes. What are these three axes and why do we need them? So, these are nothing but imaginary lines that we have drawn in our aircraft just so that we can study them better. All right. So, what are these three lines? So, firstly, we have our lateral axis. What is lateral axis? So, lateral axis is a parallel to the wing. So, it is a straight line which is parallel to the wing. In this, you can see the green line here which is going through the wing, coming out from here. So this, which is parallel to the wing, this line, this green line is what? Your lateral axis. And then similarly, you have what? Longitudinal axis. Longitudinal axis is a line, straight line, which is going through your what? Nose, passing through the nose and then going to your tail, right? So this is what? Your longitudinal axis going from nose to tail. And then you have your normal axis. What is normal axis? So normal axis is something which is going from top to bottom. So this purplish or bluish line that you are seeing is what going from your top to bottom. So this is your normal axis. All right. So we have these three axes that we have imaginary lines. So they are obviously not in the aircraft, they are just imaginary that we have made so that we can study the aircraft better. All right. And one more thing, that all of these lines they pass through the center of gravity. So all of these lines they will intersect at a common point. In this, I have not made a straight line, otherwise they would be intersecting at a common point. So this point would be what? Your center of gravity. And what is the center of gravity? You might have heard this very often, but what is center of gravity actually? Let's see. So, center of gravity, it is a point at which the aircraft will literally balance if suspended with a string. So, imagine it like this. If I have an attachment over here and I have attached my aircraft with a string, right? And I have attached it here. So, my whole aircraft will balance. It won't tip down or it won't tip up, anything, right? The aircraft will literally balance at this point. So this particular point at which my aircraft is balancing when I have suspended it with a string. So this point is known as what? Your center of gravity. You can also imagine it as a point where the whole weight of the aircraft is acting. So you can imagine it as the whole weight of the aircraft is acting at this particular point, right? And the center of gravity can move during the flight since the weight of the aircraft reduces, right? So if you know that the aircraft they need fuel to fly, right? So the fuel it burns, right? During flight, the aircraft loses the fuel, they burn the fuel, and then uh, it comes out of the exhaust and it goes to the atmosphere, right? So which makes the aircraft what? Lighter. Now the aircraft is lighter, and during flight, obviously the aircraft loses fuel and it gets lighter, right? So as the aircraft gets lighter, the CG, the center of gravity, it can change its position. All right, the center of gravity is not fixed here. During flight, it can move here, it can move here. All right, so it depends on the fuel, right? During flight, it can change. Now we have pitching. What is pitching? So pitching, again, you might have heard this thing many times, but what actually is pitching? So pitching is something that is done in an aircraft by using elevators. So we have elevators which are used for pitching. What are elevators? So elevators are these components at the end of the aircraft, the tail section of the aircraft, that are attached for the pitching movement. All right. And pitching is done on your lateral axis. All right. This is very important. In your exams, multiple times they will be asking this. So pitching is done in what? Lateral axis. How is pitching done in lateral axis? Pitching to is this movement. Many people confuse it, right? So pitching is what? Up and down. But how is it happening in the lateral movement? So you can just imagine it as like passing a rod or a pencil or anything through this body of the aircraft, and then holding it from this point and holding it from this point, and then try to rotate it, right? So then you'll see that the body started to what? Pitch, right? If you're holding it from here and here and then rotating it, then you'll see what? There is a pitch movement, right? So the aircraft pitches using elevator, and the movement is about lateral axis. All right, so this is very important for your exam. Then we have rolling movement. So what is a rolling movement? Rolling movement is done using ailerons. So these are your ailerons at the wings, right? And it is a movement about longitudinal axis. All right. So rolling is a movement about longitudinal axis. And this again is your longitudinal axis. This purplish line that you're seeing here is your longitudinal axis. And again, if you want to imagine it, you can just imagine it as like you're holding something from this point and holding one more from here, and then you are rolling it, right? Then what you'll see that the aircraft is rolling, right? So rolling is done using ailerons and it is in the longitudinal axis, again, very important. Then you have yawing. So yawing is done using rudder. What is yawing? So yawing is this motion, left and right of the aircraft. This is yawing. And it is done using what? Rudders. So where are rudders? Rudders are on your vertical stabilizers. So these are your rudders. And yawing is done by rudders. All right. And it is a movement about normal axis. All right. This is very simple. You can imagine this particular normal axis, right? And again, you're holding it from here, you're holding one end from here and you're rotating it like this. What you'll see that the aircraft is yawing to the left and right. All right. So yawing with a rudder and is a movement about normal axis. Again, important. Now, all of those movements that we have seen, yawing, rolling, and pitching, right? So all of these movements can be done by any of these three methods. So we have three methods for doing those movements. Like we can pitch with three methods, we can yaw with three methods, we can roll with three methods. What are these three methods? So first we know and we have already seen that pitching is done by what? Elevators. Rolling is done by what? Ailerons. Yawing is done by what? Rudders. So the first is what? By deflecting control surface, right? This we have already seen that when we deflect ailerons, sorry, when we deflect this elevator, then there will be a pitching movement. When we deflect our ailerons, there will be a rolling movement. When we deflect our rudder, there will be a yawing movement. So this is method one of rotating the aircraft around its axis, that is to deflect the control surface, and it is the most common method that is used widely used in all of the aircraft. We rotate the aircraft around these axes by using what? Control surface. This is the most common method, right? Apart from control surface, we have a second method too, which is by changing the angle of incidence. We'll see what and how it works. And the third method is what? By reducing the lift on one wing using spoilers. So this is the third method. We'll go in detail of one by one. So firstly, we have what? By deflecting control surface, which is the most common method. All right. So by deflecting control surface, firstly, we need to know what a control surface is, right? What is a control surface? So we have three primary control surface, right? Control surfaces are either primary or secondary. We don't need to study secondary now. We can go in details of secondary later, but the primary control surfaces are elevator, ailerons, and rudders, right? We have already taken a peek into what elevator, aileron, and rudder are, but let's go in detail. So then how do a control surface work? All right. So we have seen what elevator, aileron, and rudder are, but how do they work? How do they actually rotate the aircraft around its axis? All right. So they work by increasing or decreasing the angle of attack. All right. So this might sound a little complicated. How is it actually working? So this will see how is it actually changing or increasing the angle of attack or decreasing the angle of attack. I have made a small presentation in which I have explained it. So you'll be seeing that now. Right, so all of my control surface, be it elevator, aileron, or rudder, they all work by changing the angle of attack and camber. So how is these surfaces changing the angle of attack and camber? So let's see. For example, I draw an aerofoil, right? So this will be my wing, and then I'll attach a control surface over here.
So this is my control surface. Now this control surface can be either your elevator, it can be your aileron, it can be your rudder. So all of them have the same principle. That's why you can consider this particular part as your elevator, aileron, or rudder. Now, what is the angle of attack of this particular control surface? So angle of attack is the angle between chord line and relative airflow. So what is the chord line? So chord line will be a straight line joining the leading edge to the trailing edge, right? So if I draw a straight line, let me draw a straight line joining the leading edge and trailing edge. So this would be what your chord line, right? And what is the relative airflow? So the relative airflow is exactly opposite to your flight path. So what is the flight path? Flight path is the direction in which your aircraft is moving. So this is my wing, right? Although the wing is like this, the aircraft is moving like this, right? So you can imagine it that the aircraft is like this and it is moving like this, right? So the flight path would be what in this direction, right? The aircraft is moving in this direction like this, right? So the relative airflow will be what exactly opposite to it. So the relative airflow will be like this, right? So if I draw a few lines of relative airflow, so the air will be like this. So relative airflow is like this. All right. So what is my angle of attack? Angle of attack is the angle between relative airflow and chord line. So you can see this angle over here. This is between relative airflow and my chord line. So this is my angle of attack, right? This is when my control surface is in neutral position. All right. So what would happens if I deflect the control surface downwards, right? So now when I deflect the control surface downwards, so this is again my wing, right? And if I deflect the control surface downwards, so this would be what my control surface. If I deflected it downwards, then what happens to the angle of attack, right? So this is my leading edge. This is again my trailing edge. So the chord line would be a straight line joining leading edge and trailing edge. So this would be what my chord line, right? And what will be my angle of attack? The angle between chord line and relative airflow. Again, the aircraft is like this, but it is moving like this. So the flight path is in this direction, and the relative airflow will be exactly opposite to the flight path. So we'll draw the relative airflow now. So this will be my relative airflow, right? Now, what is my angle of attack? Again, the angle between relative airflow and chord line. So this angle is what my angle of attack. Now, if you have watched closely, then you can see that the angle of attack is increased. In our previous case, the angle of attack was smaller, but now, since I have moved the control surface downwards, the chord line has shifted and hence the angle of attack has increased, right? So by deflecting the control surface, you are increasing the angle of attack, which is increasing your lift. Again, in the third case, if I deflect the control surface downwards, then watch what happens. So I have my airfoil again. This is my wing surface. And now if I deflected the control surface upwards like this, and again my chord line leading edge to trailing edge, so a straight line joining leading edge to the trailing edge, this will be what my chord line. Now what is my relative airflow? Since my flight path is like this, sorry, my airfoil is like this, but the aircraft is moving like this, so the flight path is in this direction, so the relative airflow will be exactly opposite to it. And if I draw a few lines of relative airflow, so you can see, right? Now, what is the angle of attack between the relative airflow and chord line? So this is my angle of attack. So now the angle of attack has what? Reduced. So this case, when we have moved the aerofoil upwards, the angle of attack has reduced, right? In this case, when downwards, the angle of attack increased. In the first case, when neutral, it was decent, right? So what we get from this, when we deflect the aerofoil downwards, be it your elevator, aileron, or rudder, we get an increase in angle of attack, which will eventually increase the lift, right? Same here, also deflecting it reduced the angle of attack, which means the lift will be reduced. We have seen how the angle of attack is changing when we move the control surface, right? For all of these surface, it will be the same, right? The angle of attack is increasing or decreasing depending on in which direction the control surface moves, right? Now, how is the camber changing? So let's see what is the camber first of all. So if I have an aerofoil like this, right? So a camber is the difference between camber line and chord line. So first of all, let's draw a chord line. We know what a chord line is. So straight line joining leading edge and trailing edge. So this straight line would be what? My chord line, right? So this is my chord line, right? And there is one more line which is different from chord line, which is known as a camber line. So what is a camber line? Camber line is a curved line, right? Not necessarily always curved, but it can be a curved line which divides the wing or the which divides the aerofoil into two equal parts, right? So if I were to divide this aerofoil into equal section, like the symmetrically, if I want to divide this aerofoil, then this portion, then a line, this would be what? My camber line. So this line, this dotted line that you're seeing is dividing the upper part and the lower part in equal section. And this is a curved line. It can be a curved or a straight line. So this is my camber line. So what is camber then? So camber is the difference, the gap that you're seeing, this gap between your camber line and chord line. So this straight line was what? Chord line, and this was my camber line. And this gap that is formed between the chord line and camber line is known as what? Your camber, the camber of the wing, right? So how are we changing the camber of the wing? That we'll see now. So now, for example, if I have an aerofoil like this and my control surface is deflected, for example, downwards, right? So this is my control surface. And what will be my chord line? Again, leading edge to trailing edge, a straight line. So something like this would be what? My chord line, right? And what will be my camber line? So camber line is a curved line which is dividing upper and lower parts in equal half. So the camber line would be going something like this, right? Dividing it to equal halves, right? So it will be like this. Now see what happens to my camber. Camber is the maximum distance between the camber and the chord line. So this would be what? My camber. So this, as you can see, the camber is a lot bigger, right? But if my airfoil was in neutral position, then let's draw it. So again, my chord line, and if I were to draw my camber line, it would be almost similar to my chord line because it is already dividing into equal parts. So you can see in this case, the camber is not as much as here, right? So in neutral position, there was almost no camber. And as I deflected the control surface downwards, the camber has increased by a lot. Now what will happen if I deflect the control surface upwards? So if I have deflected the control surface upwards, and again, leading edge to trailing edge would be what? My chord line, and my camber line dividing the wing, dividing the airfoil into equal halves. So it will be something like this, right? So this will be my camber. Now, again, you'll be seeing that the camber has increased, even though we have deflected the aerofoil upwards. When we have deflected the control surface upward, then also the camber has increased. In this case, also the camber was increased. In this case, also the camber was increased. The difference is that in this, you can see the dotted line or the camber line is above. So camber line is above and chord line is below. So here you can see the chord line is below and the camber line is above. Here it is exactly opposite. The straight line, the bold line was what? Your chord line. So here your chord line is above and your camber line is below. So whenever your camber line is below, then the lift force generated will be downwards. This is always the case. If the camber line is below the chord line, your lift force will be generated downwards. And if the camber line is above chord line, then the lift force will be generated upwards. Alright. So although the camber has increased in this case, but the lift force generated will be downwards, right? So this is how changing camber can affect your aerodynamic characteristics. So we have seen now that elevator, aileron and rudder, all of them can change the angle of attack and also change the camber. And this is how these control surfaces work and you are able to move your aircraft in variety of axes.
All right, so you might have seen in that video that whenever there was a control surface and it was deflected upwards or downwards, there was a change in angle of attack, right? So if it was deflected downwards, then the angle of attack was increasing, right? The angle of attack was increasing. And if I was deflecting the control surface upwards, then the angle of attack was reducing. All right. And you know this thing that angle of attack has direct relation with lift. If you increase your angle of attack, the lift increases, right? You know this thing that whenever you increase the angle of attack, the lift increases, right? So in this case, in this particular diagram, this one, there is what your elevator, right? And your elevator has deflected what downwards, right? So in this case, what will happen whenever you move the elevator downward, the angle of attack increases, right? So angle of attack is increased, which means there will be more lift, right? So this will be lifted upwards, right? There will be more lift, so there will be a lift vector like this, right? And it will move the tail upwards, right? If the tail is moving upwards, what will happen to the nose? Obviously, that nose will move downwards, right? So this is the point. From here, you can imagine it as like a hinge. So if I'm lifting this part upwards, this will go downwards, right? So the nose will go downwards. So I have moved the control surface down. Lift has increased on this surface. So it is moving upwards and the nose is going down, right? And exactly opposite in this particular case, what is happening? The elevator is moved upwards. Since the elevator is moved upwards, the angle of attack is decreased. Angle of attack is decreased, so the lift is going like this, right? And if I'm moving the tail downwards, then what will happen? The pitch of the aircraft will go upwards, right? So this is how any of the control surface is working, right? So in this case, as we have seen, so elevator help us in pitching the aircraft, which is a movement about lateral axis. We have already seen, right? And yeah, these 2 points are very important for your exam purpose, right? So first is what control column forward. So if I move the control column forward, if I have a yoke, for example, and I'm moving it forward, then what will happen? The elevator will move down, right? So the first case, the second case, this thing will happen. If I move the yoke forward, then the elevator will move downward. And when the elevator moves down, the nose of the aircraft also goes down, right? So this is very important for your exam. They'll ask it like, if you are moving the control column forward, where will the elevator move, right? So you need to tell them the elevator will move downwards and the nose of the aircraft will also go down. All right. And whenever you move the control column aft is what backwards. If you have your control column and you're pulling it towards you, this is what moving the control column aft. So if you're moving the control column towards you, pulling it, then the elevator will move upwards and the nose will also go up. So the nose goes in the direction of your elevator movement. You can remember it like that. Then we have using ailerons. So ailerons, they help us in rolling the aircraft, which is a movement about longitudinal axis. Again, the same thing we have seen, right? It helps in rolling, which is a movement about longitudinal axis, right? Then again, they also work by the same principle that I mentioned. This exact same principle, right? If you move it downward, the angle of attack increase, the lift increase upwards, then the angle of attack will decrease, the lift will decrease, right? So this exact principle will be applying here, but the difference is that the ailerons are in pairs. So you have one aileron here and one aileron here. So you have one on each wing, and the ailerons move in opposite direction to each other. So if this aileron is moving upwards, then this will move downwards. If this is moving downwards, then this aileron will move upwards. All right. So ailerons that move exactly opposite to each other. Unlike your elevator, right? Elevator, you can see that both of them are moving upwards, right? But ailerons, they are opposite to each other. Okay. How is it that? Why is that? That is very obvious because since if you have a deflected downward aileron, then it will cause what? Increase in angle of attacks. The angle of attack increase and the lift is increasing, right? And exactly opposite you will do this thing in which your angle of attack will be decreased because your ailerons are deflected upwards. So the angle of attack is decreased, which will cause what? Reduced lift. So this you can see that in this wing there is more lift, in this wing there is less lift. So there will be a rolling movement, right? So this is how your ailerons are working. Exactly the same principle. It's just that they are in pairs moving opposite to each other. All right. Then we have what? Control column right. If you move the control column right, this again, these 2 points are very important for the exam, right? So if you move the control column to the right, then what will happen? The right wing aileron will move upwards, right? So ailerons, this for example is your wing, this is your left wing, right? And the ailerons, they can either move up or down, right? So if you turn to the right, right, then what will happen? In this wing, the aileron will move upwards. The right wing aileron will move up. The left wing aileron will move down. Okay, right wing aileron is moving up, the left wing aileron is moving down when I'm turning the control arm to the right. So you can remember it like whenever you are turning right, the right wing aileron will move up, okay, and the left wing aileron will move opposite to it, which is will move down, and the aircraft will roll obviously to the right. So if you're turning right, the aircraft will roll to the right. And if you're turning the control column to the left wing aileron will move up and the right wing aileron will move down and which will roll the aircraft to the left. All right, so this, I don't think I need to explain this. This is something you need to keep in your head. Then we have a rudder. So rudder help us in yawing the aircraft. Okay, and yawing is a movement about normal axis. Again, we have seen this, right? So if you press the right rudder, right? So rudder is you don't have to move your yoke. For rudders you have your pedals, right? So you have to push it with your feet. All right, so rudders are there. So if you press the right rudder, then rudder moves to the right. Okay, again is in exact sense. So if you press the right rudder, if you press this particular rudder, then what will happen? The rudder, the surface itself will move to the right hand side. Okay, and the tail of the aircraft moves to the left. So the tail of the aircraft, as you can see in this case, the tail has moved to the left hand side and the aircraft has yawed to the right. The aircraft, if you draw it completely, you can see that the aircraft has yawed to the right hand side. Okay, so the aircraft will obviously yaw exactly opposite to where the tail goes. So if I press right rudder, the aircraft is yawing to the right, although the tail has moved to the left, but the rudder will move to the right. Okay, again, important for your exam. If you press the left rudder, then rudder will move to the left side, right? Rudder has moved to the left. The tail has moved to the right, but the nose has moved to the left. Okay, this again, very simple, but keep that in your head for your exam. We have seen the first method, which was by deflecting control surface. We saw how the elevators, ailerons, and rudders were used to change the axis of the aircraft, right? So this was what the most common method that we use in our flights, right? But there are two more methods. So the second one is what? By changing the angle of incidence. So you'll be asking what is the angle of incidence? So that we'll see now. So, what is an angle of incidence? So, it is the angle between the longitudinal axis and the chord line. So, you know what a longitudinal axis is, right? So, what is longitudinal axis? So, in this particular diagram, you can see that this red colored line is what your longitudinal axis. It is passing from the nose to the tail of the aircraft, right? So, this is what longitudinal axis. And what is the chord line? So, chord line is a straight line joining leading edge and trailing edge. So, in this diagram, you can see what is chord line. So this is a diagram of an aerofoil. So you can see that this particular portion is what my leading edge and this particular portion is what my trailing edge. So this dotted line is what a straight line which is joining the leading edge and trailing edge. This is known as what your chord line. So what is the angle of incidence? It is the angle between your longitudinal axis and chord line. So this red line was your longitudinal axis and this yellow line that you're seeing is what your chord line. So this angle that is between chord line and your longitudinal axis is known as what? Your angle of incidence. So if you change this angle, then you can also move the aircraft in variety of axes, right? But what is written here, the angle of incidence of an aircraft wing is fixed during manufacture. Then how can we change the angle of incidence? See, so why is it written here and why am I saying that we can change the angle of incidence? It is because the angle of incidence is that we are talking about is not of the wing. We are talking about the angle of incidence of the tail, right? So the tail plane can move. Yeah, the wings are fixed. The wings do not move, right? So the angle of incidence of wings of the aircraft, as it mentioned here, the wings of the aircraft is fixed. But we can change the angle of incidence of the tail of the aircraft. How? That we'll see now. So the second method was what? By changing the angle of incidence. So here you can see in this diagram, this particular portion is what? The tail plane of the aircraft. So the whole wing of the tail plane, the whole horizontal stabilizer is able to move up and down, as you can see here, right? So this thing can change the angle of incidence, right? But this is the angle of incidence of what? Your tail plane. This is not the angle of incidence of your wing. So we are changing the angle of incidence. How? Obviously the wing is moving, so the chord line that is joining the leading edge and trailing edge, it is a straight line, so it is also moving, right? So the chord line is moving, and angle of incidence is what? Leading edge and sorry, the longitudinal axis is this, so the angle between them is also changing, right? This angle is changing because the chord line is moving up and down, right? So this angle is also varying. This is why we are changing the angle of incidence by the use of your stabilizer, right? The horizontal stabilizer, the whole stabilizer is moving, right? So this is in some aircraft, and it is known as what? Moving tail. Whenever you are moving the whole tail, whole stabilizer surface is moving, then you call it what? A moving tail. So, and also they are also known as what? Stabilizer, stabilator, sorry. Because why are they known as stabilator? Because they are a combination of stabilizer, your horizontal stabilizer, plus your elevator. As the name suggests, stabilator, right? So you have what? Elevator, because they are functioning as both your stabilizer and elevator, right? So the whole tail plane is moving, and hence the aircraft is changing angle of incidence, and hence you are able to move the aircraft in variety of axes, right? So this is what your second method of controlling the aircraft. The third method is by reducing the lift on one wing. Yes, so you can reduce the lift on particular wing. So firstly we saw was what? You are changing the axis of the aircraft by using control surface, in which you were increasing, decreasing your angle of attack and your camber, right? So by changing these two factors, you were what? Altering the lift, and hence you're able to move the aircraft. The second was what? By using, by changing the angle of incidence, right? So you are changing the angle of incidence with the help of tail plane. The third is what? By reducing the lift on one wing with the help of spoilers. All right. So you are using what? Spoilers to reduce the lift on one wing, and hence able to roll the aircraft in a particular axis, right? So this is done by using what? Spoilers. They disturb the airflow over the wing, and hence spoiling the lift. What are spoilers? So these surfaces that you're seeing over the wing, they are known as spoilers. In a 2D diagram, you can see that they literally just pop out of the wing, and what they do, they disturb the airflow. They disturb the airflow, and hence they spoil the lift, they reduce the lift, right? So spoilers, although they are the secondary flight controls, right, they are not the primary flight controls. What are the primary flight controls? Aileron, elevator, and rudders, right? So spoilers are what? Secondary flight controls, but they can be used as primary flight controls to roll the aircraft, right? So this is what we are seeing. How are they able to roll the aircraft? See, so in this diagram, you can see that we have spoilers over here and one pair of spoiler over here, right? So on this wing, we'll make the spoiler to stand up. Okay, so in this second diagram, you can see that the spoilers have raised, right? The spoiler have raised, and hence the airflow over this wing was disturbed, right? The airflow was disturbed, and hence the lift was reduced, right? So the lift on this wing was same because spoilers on this wing are not armed. So this is also, you need to remember, the spoilers have only two position. One is what? When they are extended, as you can see in this diagram, they are extended. And the second position of spoiler is what? Nothing. It is in normal position, like they are on the wings, they are not extended. But ailerons have what? Three position. Ailerons had what? Up position, neutral position, and down position, right? But spoilers have only two position, which is what? Up and in their neutral position, right? So by making the spoilers to stand up on one wing, you are doing what? You are able to reduce the lift on this wing, and hence the aircraft is rolling, right? So what is it done here? To roll right. If you want to roll right, then what you have to do? You have to raise the right spoiler up, right? As you can see, In order to roll to the right, you'll have to raise the right spoiler up, which will do what? Which will decrease the lift on this wing, which will move this wing downwards and hence rolling the aircraft to the right hand side, right? And if you want to roll to the left hand side, then left wing spoilers need to be up. Like in this diagram, you can see the left wing spoilers are up, and hence the aircraft is rolling to the left hand side. Okay. And yeah, obviously, if you are rolling to the right wing spoilers will be up, and the left wing spoiler will be on what? Neutral position, right? Because there is no other position for them to be in, right? It is either up or neutral, right? So to roll left, the left spoiler is up, and the right spoiler is in what? Neutral position. All right. So keep this in your mind. This is again very important for your exams. All right, let's see what an adverse aileron yaw is. So, in order to understand adverse aileron yaw properly, you need to know what is induced drag and parasite drag. So, induced drag and parasite drag will be covered in drags chapter, but for now, we'll do a basic understanding of these type of drag. So, induced drag, you need to just know that induced drag is a byproduct of lift. So, whenever there is an increase in the lift, right, there will be an increase in induced drag, right? You just keep this in head. Whenever you increase your lift, there will be increase in induced drag. All right. So whenever you increase lift, there will be increase in induced drag, right? And what is parasite drag? Parasite drag will be there, be it there is lift, be there is no lift, right? Parasite drag will always be there, right? So parasite drag in this diagram, you can see that you can visualize the parasite drag as there is a flat plate and you can see how much drag it is creating. But if you have a spherical ball, then there is a little less drag. If you have more made the shape more streamlined, there will be lesser drag. In this, there will be again way lesser drag, right? So you can imagine what a parasite drag is, and it will be there, be there is left, be there is no left, right? So it does not depend on left. All right. So these are the two types of drag there will be, that will be there, right? So now imagine that this is your wing, right? And you have deflected your ailerons downwards. All right. So whenever you deflect the ailerons downward, what happens to your angle of attack? It increases. All right. What happens to your camber? It also increases, right? So this together causes what? Increase in lift, the lift increase, right? And now we know that whenever the lift increases, your induced drag increases, right? So whenever you deflect the ailerons downward, your induced drag will increase, right? There will be a lot of induced drag, right? This you know now. And on top of that, there will be some parasite drag too, right? Because it is like a flat plate, right, into the airflow. So it will cause what? Parasite drag, something like this, right? So there will be drag because of induced drag, and there will be some parasite drag too, right? So this is when you deflect the ailerons downward. Now imagine you have your wing again and you are deflecting the ailerons upwards. So in this case, what will happen? So tell me what will happen to the angle of attack. Angle of attack will be what? Reduced, right? The camber will also be reduced, and this together will cause the lift to decrease, right? The lift will reduce, and since the lift has reduced, your induced drag will be reduced. So there will be almost no or very less induced drag on this wing, right? So there will be very less induced drag, and parasite drag will be there. Right? Parasite drag does not depend on lift. So parasite drag on this and on this wing will be same, but the induced drag will be more on the aileron, which has deflected downwards. Right. So this is the first case, and this is your second case. So there will be more drag on this wing because there is more induced drag, right? And less drag on this wing because there is less induced drag. Parasite drag will be the same on both the wings, right? So this you remember. I hope you have understand this concept. Now we'll proceed to understanding what adverse aileron yaw is. So in adverse aileron yaw, as I explained, that when you move the aileron downward, there will be angle of attack increase, left increase, increasing induced drag. That is exactly what is happening here. So on this particular side, on the right hand side wing, you can see that the aileron has deflected downwards. All right, the ailerons has deflected downwards, which means there is an increase in angle of attack. There is an increase in angle of attack, which means there is also what? Increase in camber. So both of these causes what? Increase in lift, and more the lift means more the induced drag, right?
So on this swing, you have what? You have induced drag, right? Also, there is always what? Parasite drag, right? As I already explained, the parasite drag will be there no matter there is left, there is no left, right? So, induced drag plus parasite drag. A lot of induced drag, right? Because there is a lot of increase in the lift. So, there will be a lot of induced drag plus there will be parasite drag. So, this is the case on this particular wing where the aileron has deflected downward. Now, when I deflect the ailerons upwards, watch what happens. So on this particular wing, the ailerons have deflected what? Upwards, which means there is a decrease in the angle of attack, right? There is a decrease in your camber, right? And which means your lift has what decreased, and lift is decreased, which means what happens to your induced drag? There will be significantly lesser or almost no induced drag, right? But parasite drag will be there as usual, right? So what do you think happens to the total drag? The total drag on this wing, on the left wing, will be lesser as compared to the total drag on this wing, right? Why? Obviously, there is more induced drag on this wing because of more lift, and there is less induced drag on this wing because there is less lift, which means there is more drag, more total drag on this particular wing, right? There is a lot of drag because of induced drag is increased a lot because of the lift. Parasite drag, although is same on both the wings, but because of more induced drag, there is a lot of drag on this wing, and because of some parasite drag and maybe a little bit or negligible amount of induced drag on this wing, there is less drag, right? So this is happening whenever you use your ailerons. So what happens is, since the aircraft was moving earlier in this direction, like the aircraft was moving like this, what happens now, since this swing is moving a lot more and this swing is restricted because of drag, the aircraft yaws to the right. In the second diagram, you can see earlier the aircraft was going like this. Now it has yawed to the right hand side. So when the ailerons roll the aircraft, it does so by increasing lift on one wing and reducing on another. This causes increase in induced drag on one wing with more lift, which causes a yawing movement opposite to the direction known as adverse aileron yaw. So now you know what the adverse aileron yaw is and how do we avoid it. So how do we avoid adverse aileron yaw? So we have four methods of avoiding adverse aileron yaw. We have differential aileron, then Frise aileron, then aileron rudder coupling, and then using spoilers for turns. So we'll see one by one what are these and how are they avoiding adverse aileron yaw. First is differential aileron. What are differential ailerons? So the upgoing aileron moves through a larger distance upwards than the amount by which the downgoing aileron moves down. So in this you can see that the aileron has moved upwards and the amount by which it has moved upward is more than the amount by which it has moved downward, right? So the aileron is designed in a way that they are moved upwards more than how much they move downwards, right? Why is it done? So it has a very simple reason. See, the airflow will be coming from here. It will be hitting the surface. So there will be a lot more parasite drag on this particular wing, right? So there will be more parasite drag on the aileron which has moved upwards, right? So there will be more parasite drag, obviously, because we have seen how the parasite drag works. There was spherical, and there was a streamlining shape, and there was a flat plate. So you know how the parasite drag works. We'll go in detail in drag chapter. Don't worry about that now. But there is more parasite drag on this upgoing aileron, right? And significantly lesser parasite drag on the downgoing aileron because the parasite drag is again there will be a smoother airflow over this particular section of the wing, so there will be lesser parasite drag because we have moved the aileron downwards by a lesser amount, right? So what we have done, we have increased the parasite drag on upgoing aileron and reduced the parasite drag on downgoing aileron, right? So how is it helping in reducing adverse aileron yaw? So see what and how we reduce it. So what we did, we moved this aileron downwards by a lesser distance. So this aileron was moved down by lesser distance. So induced drag was there, no doubt, induced drag was there, but the parasite drag that was also adding to the total drag was reduced. The parasite drag is reduced here. And in this side of the wing, what we have done, we have moved the aileron upwards by a larger distance, which means what? Induced drag was already less, but it was there.
and the parasite drag has increased. We have increased the parasite drag on this wing. So the parasite drag on this wing has increased, which means there is more drag, more total drag on this wing, right? So there will be more total drag, and here the drag was also reduced because there was more drag on this wing. That's why it was yawing to the right. So what we have done, we have increased the drag on the left wing, right, by increasing the parasite drag, and we have reduced the drag on the right wing by reducing the parasite drag, and hence the total drag is now balanced, right? So the aircraft will not yaw in this direction; it will continue in the direction it was. So this is how the differential aileron works. Second we have is Frise aileron. So Frise aileron does is they have this extra surface under the aileron. So whenever the aileron moves upwards, this extra surface, this red portion that you're seeing, it protrudes outwards in the airflow and disturbs the airflow. So this again is increasing your parasite drag. So whenever the aileron moves upwards, there is an increase in parasite drag, right? So this again helps in what? Your increasing the parasite drag will increase the total drag on the left wing that we saw, the upgoing aileron, right? So there will be more parasite drag on this wing, which means more total drag, and hence again balancing out the drag between the wings, right? So whenever the aileron moves upward, the increase in the parasite drag is there because of this particular surface that you're seeing, right? It protrudes outward into the airflow, right? And whenever the aileron moves downwards, there is no such surface attached here. So the smooth airflow is there. So there is no increase in the parasite drag when the aileron moves downward. Then you have aileron rudder coupling. This is again very simple thing. So what we do is we just couple the aileron and rudder together. So whenever we move the aileron, as we move the aileron, the rudder automatically moves. It should be rudder. So whenever we move the aileron, the rudder automatically moves and it counteracts the adverse yaw. So it will move obviously in the opposite direction so that the rudder will uh, able to counteract the adverse aileron yaw. So it will be paired. So whenever you move the aileron, there will be a slight movement of the rudder too, which will counteract the yaw. All right. Then we can use spoilers for turning, or sorry, for rolling. It should be. So whenever we use spoilers, right? We have seen how we turn with the elbow spoilers. It reduces the lift on one wing, right? So spoilers do not produce any adverse aileron yaw. Why? Because obviously adverse aileron yaw started from the production of lift. Whenever there was lift, increase in the lift caused increase in induced drag, which caused more drag on one wing and less drag on another, which causes adverse aileron yaw, right? But if we use spoilers, there is no increase in lift, right? This equation is out of the this is out of the equation, right? There is no increase in the lift, which means there is no increase in the induced drag. Why? Because spoilers they work by reducing the lift. So whenever there is a reduction in the lift, there won't be any induced drag, right? There won't be any induced drag, so there won't be a problem of difference in the drag of the two wing and then causing opposite yaw. So if we use spoilers, there will be no adverse aileron yaw. Since spoilers cannot increase lift, they produce drag only on the wing. They are extended, hence there is no adverse aileron yaw, right? Then there are two different type of ailerons in the aircraft. One is inboard and another one is outboard. So most of the modern jets they're fitted with two sets of aileron. One is inboard. So these that you're seeing are your inboard ailerons. These and these are your inboard ailerons, and outboards are fitted at the outboard, obviously at the tip of the tip section of the wings, right? So what are the purpose of these? So at the lowest speeds you're supposed to use inboard and outboard both. You can use inboard and outboard ailerons together at lower speeds, right? But at higher speeds, you're supposed to use only your inboard ailerons, right? Whenever you're at high speeds, only use inboard ailerons. Why is that? It is very simple. Like if you imagine you're bending something from here, right? If you are bending the wings from here, then it will be easier for you to bend the wings, right? But if you're trying to bend the wings from here, if you're holding the wings from here, you're trying to bend it, will be difficult. Why is that? In terms of physics, it is because of the moment, right? So if we take your center of gravity here, we measure the moment will be lesser because moment is what? Force multiplied by distance. So the moment will be lesser if we are trying to bend from here, which means it will be tougher for us to bend the wings, right? But if we are trying to bend it from this portion, then the moment will be larger because moment is what? Force into distance. Even though force is same, but the distance is increased, right? So this distance is increased, which means the moment will be larger. So if we are trying to roll the aircraft with the help of outboard ailerons, then there will be higher bending moment of the wing, right? And at higher speeds, this force will also increase, which means there will be a lot more bending moment of the wings, right? So this can break the aircraft, right? This can break the aircraft wings, right? So at lower speed, it is fine. The force is in control and you can use any of the distances, any of the inboard or outboard. You can choose any of them. The total movement will be still in control. But at higher speed, the forces also increase. So you need to take a shorter distance. Yani ki you need to take a smaller or a aileron which is closer to the CG. So the distance will be lesser, so the total movement will again be in control, and hence your aircraft will not have too much wing bending, right? So this is again a very important question for your DGC exam that at lower speed you can use both inboard and outboard, but at higher speed you are supposed to use only inboard. And generally at higher speed means that most of the modern aircraft is like that whenever you retract the flaps, whenever the whole flaps are retracted, that is after takeoff, whenever the whole flaps are retracted, then you're supposed to use only inboard. The outboard aileron then comes to a locking position. These aileron get locked, and you are able to use only inboard ailerons for turning the aircraft or rolling the aircraft. All right. Then in some aircraft there is aileron drooping. What is aileron drooping? So in some aircraft, both the ailerons are deflected downwards so that they can act like flap and provide some extra lift. So it is nothing, it's just this portion that you're seeing here, this is aileron, but ailerons are there for turning in opposite direction, right? So you have an aircraft, you have one wing here, you have one wing here. So if this aileron is going downward, this aileron will go upwards, right? This is how the ailerons work normally. But in some aircrafts, what they have done is they have moved the ailerons downwards together. So what it helps as they work like flaps. Flaps, I think we have covered. No, if we haven't, then flaps are what they increase the lift at lower speed. They are therefore increasing the lift at lower speed, right? So this uh, symmetrical movement of aileron, which works like flaps, can be done, which is known as aileron drooping. In most of the Airbus aircraft, it is there. So they provide some extra lift during the takeoff phase of the aircraft, and then they can be switched to your aileron mode again, operating in what asymmetric mode, which the aileron and the aileron surfaces will move opposite to each other, right? So in just for your takeoff section, this is done aileron drooping so that you can get some extra lift by deflecting both of the ailerons in the same direction, right? So they can work like flaps, right? Then we have some special flight controls. So what are these special flight controls? We have elevons. What are elevons? Elevons are a combination of elevator and aileron. You don't have to mug up any of these. They literally make sense. Elevons, so elevator, and ailerons, elevons, right? So it is a combination of elevator and aileron. You might have seen these delta wing aircraft in which there is just one surface which does the function of both elevator and aileron. So if you move them together in the same direction, it will work as what? Elevator. Both of them moving downwards will work like a elevator. Both of them moving opposite to each other will work like a aileron, right? So these are what? Elevons. You also have ruddervators. Ruddervators is a combination of rudder and elevator. They are used in V-tail aircraft. So this image that you're seeing here is a V-tail aircraft because the tail is in a shape of V, right? So the rudder itself, they work as both rudder and elevators, right? So this surfaces, they can work like rudders and elevators, known as ruddervator. Then you have a stabilator. We have already seen what a stabilator is. So the whole horizontal stabilizer was working like a stabilator. So it works like a stable horizontal stabilizer and an elevator. And then you have flaperons. So flaperons are a combination of flaps and ailerons. So they work like flaps and ailerons. Again, this is important for your exam and it is very basic, so I don't need to explain this. You can just remember these names and you can find out what combination it is of, right? Then there is something known as center of pressure. So why am I teaching you center of pressure in aircraft systems? Because it is important to understand the topics that we'll be covering next. So center of pressure is a point at which the total average lift is considered to be acting, right? You know, this is our aerofoil, right? So the lift acts perpendicular to your relative airflow, right? So imagine it like this. This is your aerofoil. So there will be air flowing from here, 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 here. And the lift will be perpendicular to these relative airflow. So this will be like this, lift will be like this, lift will be like this, lift will be like this. So what we do is we, just for studying purposes, what we do is we combine all of them, all of the lifts, and we find out the average lift, right? And then we call this average lift the point that where the average lift is acting as the center of pressure. This particular point is known as the center of pressure, right? Center of pressure moves forward as the angle of attack increases. You don't have to go in detail of why is it happening now, because this is a part of principle of flight. But the center of pressure moves forward as you increase the angle of attack, because the total average lift will be moving forward, right? So this is the center of pressure. All right, so what is aerodynamic balance? So aerodynamic balance is a method of reducing the pilot's efforts to move the controls. So you can see in this image clearly that the pilot is struggling. Why is he struggling? He is struggling because he is not able to move the controls, right? So why does this happen? It happens because, see, let's take your horizontal stabilizer and let's take your elevator attached here. All right. So there will be a lot of air that will be moving over these surfaces, right? So there, because the aircraft is flying at high speeds, right? And there will be a lot of air. So the pilot in a smaller aircraft mostly is the controls becomes very stiff because the pilot is controlling it with a yoke which is connected with pulleys and cables to your control surfaces, right? So it becomes very hard for the pilots to move the controls, right? So these forces that pilot having to apply needs to be reduced in order to avoid pilot fatigue, right? The pilots will get fatigued with because they have to do such long flights, and if they have to apply such high forces all the time, so they'll get fatigued, right? So aerodynamic balance is a method which we imply to reduce the pilot's effort to move these controls, all right? And you can see that if these forces are in a limit, it is a good thing. But because it provides feel to the pilot. So what is feel? Feel is obviously it gives a sense of control, right? If the pilot are, for example, pulling the yoke, they need to able to feel. And when will they feel? When the yoke is trying to resist the movement, right? If the yoke is having to, if the pilot is having to apply almost zero forces, if the yoke moves like literally like magic, the pilot just touches it and the yoke moves. So this is also something which is not good, right? So the pilot is having to apply a lot of force, that is also bad. But if the pilot is having to apply all zero force, that is also bad. The pilot, when he applies the reasonable amount of force and the control column or the control surfaces move, that is a good thing, because the pilots can feel the controls are being moving, right? If there is zero feel to the controls, then what will happen, that the pilot might over control the aircraft, right? So that is why there has to be some feel to the control, but not too much, right? Hence aerodynamic balance is reducing the pilot's effort and not putting it to zero, right? That is also a bad thing. So too much efforts, bad. Little effort, good. Zero effort is again bad, right? So how much forces do a pilot need to apply? So pilots need to apply enough force to counteract the movement of the control surface, right? So what is the movement of the control surface? So movement we know is force multiplied by distance, right? And the greater the movement, greater will be the force required by the pilot. So how much force does a pilot need to apply? It depends on what? Movement. So more the movement, more the force required by the pilots, right? So what is the movement? It is force into displacement. What is this force? So the force is this. This is the force. This is what? This is your lift. So this force that you are seeing here, this is what? A lift vector, right? And lift is acting from what? This is acting from your center of pressure, right? So CP is here And what is this distance? So distance is always taken from your hinge. So this is your hinge. Hinge is what? Nothing, just a point from which this is moving, right? It's a hinge, right? So the distances are taken from the hinge, and this is your center of pressure. So from the your hinge to your center of pressure, this is considered as your distance d, and the forces or the lift vector is considered as your force F. All right, so the movement of the control surface would be how much force multiplied by distance, right? And the force depends on what? Since the force is what? Lift. Force is here means lift, right? So it depends on what? It depends on your exact lift formula, half rho v square cl dot s. So your force will depend on your angle of deflection. Angle of deflection is nothing but your angle of attack, right? Your angle of attack increases if you increase the angle of deflection. So in CL, it comes as angle of deflection. You don't need to go in details right now. This is all principle of flight. So just know that movement is this, and it is force into displacement. The pilot need to counteract this movement by the control. This is all you need to know for now, right? And size of controls, it depends on size of control. Is if you increase the size of this control, then also the force vector will increase. So this force will increase, right? And and that is also in the equation. And if you increase the speed, that is if you increase the velocity, then also the lift will increase, which will increase your force, right? The force will increase. And the distance d is taken from the hinge of the control surface. This we have already seen that from the hinge to the center of pressure is what? Your distance. All right. So the methods for aerodynamic balance. What are the methods by which we reduce the pilot's effort to move the control? So these are all of the methods. So we have two types. So first is we have a section of setback hinge, on balance method, and internal balance method, right? And then we have some tabs. What are tabs? We'll see. So we have balance tab, anti-balance tab, servo tab, and spring tab. So all of these together are there for what? To reduce the pilot's efforts to move the controls, which is known as aerodynamic balance. All right. So what is a setback hinge? Right. So setback hinge is during manufacture, the hinge is placed far behind the leading edge of the control surface so that it is closer to the center of pressure. Right. So see, what is our purpose? We want to reduce the pilot's effort to move the control, right? And how much efforts do a pilot need to apply? It depends on what? It depends on moment, right? It depends on movement of your control surface. And movement is how much? Movement is always force multiplied by the distance. So if we reduce the movement, then the efforts required by the pilot will also be reduced, right? So how do we reduce the movement? We can reduce it by reducing the force or reducing the distance, right? So in this particular case, what we have done is we have reduced the distance. How have we reduced the distance? So distance is reduced by moving this hinge backwards. So in the first diagram, you can see that the hinge is placed here, right? In the second diagram, you can see that the hinge has moved a little forward, right? So now the hinge is placed here instead of here, right? So the distance d has reduced, right? How is the distance reduced? Obviously, because we take the distance from what? Your hinge to your center of pressure. This is the distance. And here, since the hinge is here only, so this is the distance. The distance has reduced, means this distance has reduced, and hence our total movement is reduced. Force will be same, but the distance is reduced. So our movement has reduced, right? Which means the pilot having to apply forces will also be reduced, right? So this results in the distance d. This reduces the distance d and hence reducing the moment, right? Which was movement is what? Force multiplied by distance, right? And setback hinge. This method does not affect the control effectiveness. What is control effectiveness? As the name suggests, control effectiveness is just how effective your controls are. So you need to remember this one thing: control effectiveness will only be affected when the forces are changed, right? So moment was what? Moment was force multiplied by distance. In a setback hinge, we change the distance, right? So whenever we change the distance, there won't be any effect on control effectiveness, right? But if we are changing the force, then control effectiveness will be affected, right? So why? Because obviously I have not applied a reverse force, like this surface is trying to move upwards, right? So it is applying a force upwards. But did I do something to apply force in the opposite direction? No, I did not do anything like that. So my control effectiveness is not at all affected, right? And the manufacturer should make sure that the CP never moves too close or ahead of the hinge. This can result in no feel or reverse feel. So this is very dangerous. What happens if you're saying that okay, move the hinge backwards, it helps, right? So why not move the hinge all the way back here or all the way here? Why not do that? So it is very, very bad because the center of pressure, we know that the center of pressure should always be behind the hinge line. Why? Because see, the moment or the forces the pilot needs to apply is what again? Force multiplied by resistance. So this is the forces that a pilot need to apply, right? And as I have already mentioned that the forces are bad if they are too high, right? And they are bad if they are zero, right? But they are good if they are in minute amounts, right? So we don't want that the forces go to zero, right? This movement should not go to zero. If this movement go to zero, then the pilots will have obviously no feel, right? So what happens is if the center of pressure earlier diagram was somewhere here, right? So we were calculating the distance d and then we were calculating the moment, right? But if the center of pressure moved ahead and ahead and ahead, and at a point it will come to onto the hinge, right? So the center of pressure, if it comes onto the hinge, if it comes over the hinge, so in this case you can see the center of pressure, the force is on the hinge. So if this is the case, then the distance d will become zero, right? D will become zero because there is no distance between the hinge. D is what always taken from hinge to the force to the center of pressure, right? So if the distance becomes zero, if the distance is zero here, then your movement also becomes zero. If your movement is zero, then the force required by the pilot will be zero, and that is a bad thing, right? The pilots will have to apply zero forces, which means they can over control the aircraft, which is a bad thing, right? So this should make sure by the manufacturer should make sure that the CP should never be able to move to the hinge line. So they need to design the hinge to a point where they are sure that the CP can never come up to this point, right? So they cannot make the hinge here, right? Because they know the CP can easily move right ahead of the hinge line. And yeah, if it moves ahead of the hinge line, then the distance will come out to be negative, and this will result in a negative movement. And if the movement is negative, then what will happen? You will feel reverse feeling, right? So if you are uh, when you pull the control column, then in normal cases what is supposed to happen, the control column will try to resist you, it will apply a opposite force, right? So you will be resisted by this force, right? This is a good thing, right, if you have smaller forces. But if for example you are trying to pull the control column and the control column automatically starts to come towards you now, so this is a bad thing, right? This is very, very dangerous, right? The controls will automatically come towards you. You from your side will have to apply opposing force to stop it, right? So this can happen when the CP is moving ahead of the hinge line, right? And if it is on the hinge line, then what will happen? Your control forces will come to zero and you will have no feel of the controls. All right, so next is a horn balance method. So a horn balance method, we use a horn. What is a horn? So this portion that you're seeing, this portion which is ahead of the hinge line, this is known as a horn. We have one horn on this side and we have another one on this side. So these are just flying control surfaces which extend forward of the hinge line. So we have these surfaces which are extending forward of the hinge line. So the hinge will be what somewhere here, right? This is from where the elevator is moving, right? So this is the hinge line, and these surfaces are ahead of the hinge line. All right. So in this diagram, you can see that this portion is what your horizontal stabilizer. This is your hinge. And earlier, what we used to do is we used to have an elevator or any control surface like this, right? This is all we had, right? This much. But now we have extended this further and we have made a horn, right? So this portion is what your horn. So what it does is uh, whenever there is any surface behind the hinge. So this is the hinge, and if we have any surface behind the hinge, so this particular part will be what? This will always oppose the pilot. So this will generate a movement like this because there is force, right? And there will be a movement because of the distance of this hinge and this force, right? So there is a distance d, right? And there is a force F. So it will generate a movement like this. Okay, and this movement will oppose the pilot. Okay, but any surface which is ahead of the hinge line will produce a movement which will help the pilot or assist the pilot, right? So any surface which is ahead of the hinge line, so we have a surface here, so we have a force generated at a distance d. This is the force, right? This blue line is the force, and this is generated at a distance d. So this will also generate a movement, but this will generate a movement in the opposite direction. So it will help the pilots, right? So any surface which is ahead of the hinge line, the moments generated by surface which are ahead of the hinge line will always assist the pilot, and the moments that are generated after the hinge line will always oppose the pilots, right? So this is how the horn works in a horn balance method. And this method also does not affect your control effectiveness, but the drag is increased. Obviously, the drag will be increased because of the extra surface that is being coming into the air. So there will be more parasite drag, right? But this does not affect control effectiveness. Again, we have, although we have changed the forces, right? Moment is what? Force multiplied by distance. And I told you that whenever you change the distance, it is fine. The moment, sorry, the control effectiveness will not be affected. If we change the force, then the control effectiveness will be affected. But in this case, although we have changed the force, but the direction of force is still in the same direction, right? The force that is generated here is in the same direction as the force that was generated by the control surface. So this will again not influence the control effectiveness. If there is a force that is generated opposite to the control in the direction where the control surface is trying to make the force, then it will what? Affect the control effectiveness. So horn balance also does not affect your control effectiveness, right? Then you have a internal balance method. So internal balance method is a very awesome method, like because it does not increase the drag and it also does it purpose. So in this method, we use pressure difference above and below the control surface, and right, and this is very effective method since it does not increase the drag. It is completely internal, right, and it also does not affect control effectiveness. So how does it work? See, this what you are seeing is your tail section of the aircraft or your wing, right, and this is your elevator, right. This is your elevator. Now there are certain vent gaps. So this is a gap. There is a vent gap over here and there is a vent gap over here. So the air can pass through these vent gaps. And there is a assembly over here. This is a little complicated assembly which we don't have to go in. But what happens is there is obviously when if you deflect the control surface downwards, there is obviously high pressure here, there will be high pressure here and there will be low pressure here, right? So this high pressure air, they'll go in through this vent and they'll go and they'll try to hit this particular part, right? They'll try to hit this particular part, and since there is low pressure here, the low pressure will also be here because there is a vent here, so low pressure will be here, and there will be a force from high to low, right? So the force will be something like this, right? And this is in the case when I move the elevator surface downwards. So watch this particular clip, you'll have a better understanding how is it working. So see, I'll move the elevator downwards and you see, because this portion has moved upwards and we were also applying a force upwards, right? So this assisted the pilot in moving the control surface, right? There was high pressure here, the air moved from here, it was helping. Already the air was also pushing this particular part, right? And when the elevator was moved downwards, this particular air is holding it in that position, right? From high to low, the air is moving and it is holding this elevator in this particular position. So this is how this internal balance is working. And you don't have to actually go in the working. If you didn't understand it, that's completely all right. But you need to know that this is a very effective method as it does not increase drag and it is completely internal. This is all you need to know. If you didn't understand the working, that's fine. And if you want to, you can just rewind the video, watch it again. You'll definitely understand it. All right. And yeah, this method also does not affect control effectiveness. Again, the force is although generated, but it is in the same direction as the control surface. So there is no change in the control effectiveness. The controller is still effective. And now we have seen all of these methods that were affecting the control effectiveness. And we had stick setback hinge, we had horn balance, and then internal balance. All right. And just for a quick revision, setback hinge, the hinge was placed behind, right? So what it did, it reduced the distance and hence reduced the moment. And lesser the moment, lesser will be the force applied by the pilots. Horn balance method, we had a surface ahead of the hinge line. This surface, whenever there is a surface ahead of the hinge line, it produces a movement which assists the pilot, right? And then there was internal balance method we just saw, right? That it was working with the help of pressure difference above and below the control surface, right? And hence it was assisting the pilots. And then we have what tabs. So we'll go in details of one by one. What are these tabs? We have balance, anti-balance, servo, and spring tab. So tabs are what? All of these previous methods was reducing the control effectiveness by applying a force forward of the hinge line, right? As we saw in the first one, setback hinge setback hinge was just a simple method which was reducing your force and distance, so it was reducing your distance, right? And hence reducing the moment. The second method and the third method was horn balance and internal balance. So all of these methods was doing what? They were applying forces ahead of the hinge line. So this there was force applied here, and even in internal balance it was the same thing. So all of these methods that we saw, these three methods, setback hinge, horn balance, and internal balance, in all of them there was force applied ahead of the hinge line or the forward of the hinge line, right? But tabs, tabs are something which are attached at the rear section of the control surface. So tabs are attached the rear section of the control surface. So these little things that you're seeing here, these are your tabs. They are attached at the rearmost surface of your control surface. This is your control surface, and tabs are attached at the most rear end. So these are very small control surface by themselves. We'll study what tabs are. So we have four types: balance, anti-balance, servo, and spring. So balance tab. In this, we have our wing surface over here. This is your elevator. All right. So this is your elevator. And then this small surface that you're seeing, this is your tab. All right. So there are multiple linkages. This you can see, this is what the pilot input is. This is again, this portion is connected to your tab, right? So all of these linkages are there, and the pilot does not have the direct control of the tab. So pilots, as you can see, the pilot will be pulling here, right? And this thing will move the your elevator upwards, right? The elevators will be moved upwards. The pilot is controlling what? Pilot is controlling your elevators, right? And when the elevator has moved up, then because of this particular linkage, you can see that the balance tab has moved downwards, right? So the control surface was moved up. This was done what? Done by what? Pilot, right? And since the control surface moved up, the elevator moved up, and the balance tab, since it was attached with these linkages, it moved downwards. So this is the balance tab, and you can see it has moved downwards, right? So pilot does not have a direct control of the tab. Pilots cannot control this tab directly. So pilots control the elevator or the control surface, and the control surface then controls your tabs. All right. So pilot moves the control surface and the control surface moves the tab, right? Tabs move in the opposite direction to the control surface. So this balance tab, this these are actually the most important points for your exam. So you need to exactly write them as it is, right? And remember them. So tab in a balance tab moves opposite to the direction of control surface. As you can see, the control surface here has moved upwards, but the balance tab has moved downwards, right? So the balance tab moves opposite to the control surface. And the effectiveness is reduced in this case because there is a force generated in the opposite direction. So see, watch closely, as you can see that since the pilot has moved this particular surface upwards, hence it is generating a force downwards, right? It's generating a down force. So this is the force that the pilots want to generate, right? But what is happening, since to reduce the control forces, the balance tab, it has moved downwards, exactly opposite to our flight control. And hence, since it has moved downward, the angle of attack increased and it is generating a force upwards, right? So it is generating a force opposite to the direction the pilots wanted to generate, right? So the control effectiveness in this case has reduced, right? So the first tab is our balance tab, right? Balance tab is controlled by what? By pilot control the flight control surface, and the control surface is then controls your balance tab, right? And the tab moves in the opposite direction to your control surface, and the effectiveness is reduced. This is all you need to know about the balance tab. Then we have anti-balance tab. So anti-balance tab, the pilot does not have a direct control of the tab. Again, the pilot is moving your control surface. So this is the control surface and this is your tab. So the pilot in this case also is moving your control surface, right? So this is the pilot input, right? And it is attached to what? Your control surface. The pilot is moving the control surface. As you can see, the pilot has moved this control surface upwards, and this has deflected the the anti-balance tab in the same direction this time. So you can see the tab is reflected but is in the same direction. The elevator has moved upwards, your control surface has moved upwards, and your tab also has moved upwards, right? So the pilot moves the control surface and the control surface moves the tab. The tab moved in the same direction. So anti-balance tab, although the name is anti-balance, it is moving in the same direction. All right, to the control surface, and then they are used to increase the stick forces, right? This is a very different type of tab. So till now we have seen aerodynamic balancing, that it was to reduce the pilot's effort, but anti-balance tab is there to increase the pilot's effort. Yes, so why do we want to increase the pilot's effort? So in aircrafts with larger controls, what happens, that aircrafts with stabilator we have seen, right, the all moving tail. So in those kind of aircraft, if they are flying at high speeds, what happens, that the pilots can over control the aircraft, because we know movement is force multiplied by distance, right? And we have seen our control surface, right? And the force that it was generating. So we know that moment is force multiplied by distance. And at high speeds, force becomes very, very large, because force is what? This force is dependent on what? Your lift. So this force is dependent on your lift. Obviously, as I already told, that the force is what? Lift, right? So at high speeds, the lift increases, because lift, in lift equation, we have what? V square, half rho V square CL dot S, right? So V square, which means you increase your lift, if you increase your velocity, the lift will be increased, right? So lift increases a lot means this force increases a lot at high speed, which means your moments will be a lot. So even with the slightest movement of the control column, there will be a large movement of the airplane's attitude, right? Hence, there has to be something which resists the pilot from moving those control so much, so that the pilot may over control the aircraft, right? Or even in aircrafts that have very big control surface, very large control surface, if an aircraft have, then also the forces become very large and the movement becomes very large, which means that the pilots can over control the aircraft. So in those kind of aircraft, we use anti-balance tab to avoid over controlling the aircraft, right? So at high speeds, pilots can over control, and hence anti-balance tabs are required. And the most important points are that the pilot does not control the tab, and the pilot moves the control surface. The control surface moves the tab, and it moves in the same direction. It is there to increase the stick forces, and it is used in what? Aircrafts which have large control surfaces or they fly at high speeds, right? Then servo tabs. In servo tabs, the pilot does have a direct control of the tab. So earlier, those two tabs, balance tab and anti-balance tab, the pilot was moving the control surface and the control surface was moving the tab. But in this case, you can see that the pilot is having a direct control of the tab. You can see that this is connected directly to the tab, right? So pilot is having a direct control of the tab. So in this, the pilot moves the tab and the aerodynamic forces on the tab moves the control surface. So this is a little interesting. You see, the pilot will move this tab. So here in the second image, you can see the pilot has applied pressure here and pilot has moved the tab downwards. So the tab has moved downwards, right? And because the tab has moved downwards, there will be aerodynamic forces. The air will be flowing from here and the air will create a force on the tab, and the tab itself will move the whole control surface with itself. So the tab controls the control surface. Pilot controls the tab. So pilot is controlling the tab and the tab is controlling your control surface, right? And the control surface is moving in opposite direction to the tab. So again, your control effectiveness will be reduced, right? Then we have yeah, in servo tabs itself, the pilots need to be very aware when they do their pre-flight inspection. Why? Because in aircraft fitted with servo tabs, what happens? The pilot must make sure pilot must make sure to physically inspect if there is any control lock fitted, since the control column can be moved freely even with the control lock fitted. So what happens if I install a control lock on my elevator, for example? What are control locks? So they are just there to lock the controls in case you are deciding to park your aircraft for longer periods or there is gust and all. So you don't want the gust to be moving your control surfaces, right? So they can get damaged. So that's why what do? You lock them, right? You lock the control surface, and before flight, obviously you're supposed to take these off, because if you don't, then the control surface will not move, right? And it is very, very dangerous. So the control surfaces are there. And what happens with a servo fitted tab? So if in cockpit you have your yoke, you're trying to move it forward and backward, so your yoke will move freely, right? So sitting in the cockpit, you will think that your aircraft is ready to go because the yoke is moving, which means the elevator is obviously moving because they are connected via linkages and all, right? So you'll be thinking that the elevator is moving, right? But in a servo fitted aircraft, what happens is you're not directly moving the elevator, right? So this is the elevator and this is your tab. So what the pilot is thinking that he is moving the elevator and the elevator is working fine because it is not locked. He'll think that it is not locked, but actually it is locked. The elevator it's locked. The pilot is not controlling the elevator, he's controlling the tab, right? So the tab is moving up and down and not the elevator. So he's thinking that he's ready to go, but actually there is control locks actually fitted in your elevator, and it can be very dangerous. So the pilot need to physically inspect if the control locks are fitted, otherwise it could lead to a very dangerous situation, right? Then there is spring tab. So a spring tab, it is a balance tab with a spring mechanism. So it is exactly like a balance tab. There is no change, right? So it is just a balance tab, but it has a spring mechanism. What is a spring mechanism? So spring mechanism is there. So at lower aerodynamic forces, the spring does not compress and the pilot feels the complete aerodynamic force. So you can see this is the spring mechanism over here. The pilot is applying forces from here. So when the pilot pulls on this particular part, then what will happen? These springs that you're seeing over here, they will tend to compress, but they don't compress until the pilot applies too much load, right? So in the second image, you can see that the pilot has applied forces, but he has not applied too much forces, right? If the forces are low, the pilot has applied low forces, which means that the spring will not compress. The spring will still be there, and the spring will not compress, which means that the your tab, your spring tab will still be in the neutral position, right? But if the pilot is having to apply a lot of forces, if the pilot is applying a lot of forces, then this spring will compress and hence it will move your tab. So it has deflected the tab. So this allows what? Some forces to be there. As I said, that some forces are okay, it is good, but if there are too much forces, then it is bad. So little forces, it will let the pilot feel those forces, right? So for good feel, it will be helpful. And now if the forces are too much, then it will make sure that the tab is in action and it is able to assist the pilot. Then what is mass balancing? So this is another type of balancing. Early what we saw, first of all, what we saw was what? our aerodynamic balancing, right? So what is aerodynamic balancing? It was there to assist, to make sure that the pilot do not have to apply a lot of forces on the control column. It is easier for him to move the control surfaces, right? So the next type of balancing is what? Mass balancing. So mass balancing is what? It is exactly, it is really, it does not have any common, there is nothing common between mass balancing and aerodynamic balancing, because they are very, very different. So don't confuse them. Mass balancing is a type of balancing which is done, which has nothing to do with reducing stick force, right? And it is a method of reducing flutter. So mass balancing is done to reduce flutter. A very, very important question for your DGC exam. Mass balancing is there to reduce flutter, and it is known as what? Mass balance. So method of reducing flutter is known as what? Mass balancing. So what is flutter? First of all, flutter is nothing. It's just uncoordinated oscillation of control surface coupled with bending and twisting. So flutter, you all already know that when something is moving up and down or is oscillating like very, very fast or vibrating very, very fast, so that is known as flutter, right? And if that is happening to your control surface, then it can cause serious damage to the control surface. And why does flutter happens at the first place? So the flutter occurs when the CG, or center of gravity, we already know what it is, right? So center of gravity of the control surface is behind the hinge, and hence CG should always be on the hinge line. So in this case, the first diagram that you are seeing, this is the center of gravity, right? And center of gravity should never be behind the hinge. So this is your hinge and your center of gravity is here, right? So center of gravity, if it's here, then it can cause flutter. The airframe or the surface will flutter like crazy, right? So this CG should never be behind the hinge line, or else what will happen? Flutter, right? So CG should be where? On the hinge line. So the CG should be from moved from here on the hinge line. Now this is a perfectly safe condition to fly. So the CG of the control surface should be on the hinge line and not behind the hinge line, or else there will be flutter. And don't confuse it with CP. CP was different. So CP should always be behind the hinge line. If CP is on the hinge line, then what happens? The movement becomes zero. The moment becomes zero, and you have to apply zero forces. Or if the CP moves ahead of the hinge line, then what happens? You get a reverse feeling, right? So that is CP. That is center of pressure, which is different from CG, right? And so CP should always be behind the hinge line, but CG should always be on the hinge line. All right, don't confuse it with this. And this is again very, very important for your exam. All right, so that is it for this particular part. I know flight controls is a pretty vast section to cover in one video, so I'll make a second part on this and keep making your notes, revising them, and that's it. All right, bye bye. Enjoy.